Welcome to non-homogeneous linear second order equations. So first off, let's just do some theory. So we do have an existence and uniqueness theorem for non-homogeneous linear second order differential equations. So let's consider the IVP. Y double prime plus P of X times Y prime plus Q of X times Y equals F of X with initial conditions Y of X naught is equal to K1 and Y prime of X naught is equal to K2. Here, X naught, K1, and K2 are all real numbers. Then if P, Q, and F are functions involved in our differential equation, are all continuous, on the open interval AB, then there is a unique solution to the IVP on the interval AB. So this is more or less the exact same existence and uniqueness theorem we've seen previously for linear differential equations, that the equation must be written in the form such that the highest order derivative has a coefficient of 1. And then we can just look at all of the other functions acting as coefficients and the function on the opposite side of the equation, as long as those are continuous. On an open interval containing our initial x, we should have our existence and uniqueness of a solution. So now we're going to move on just to the general solution. So let's go ahead again and consider the equation y double prime plus p of x y prime plus q of x y equaling f of x. And we'll say with P, Q, and F continuous on interval AB. Now let's suppose that YP is a solution to the equation. We often refer to this as the particular solution. Hence Y sub P. And now let's suppose that Y1 and Y2 form a fundamental set of solutions. To the corresponding homogeneous equation. Y double prime plus P of X times Y prime plus Q of X times times y equals 0. Then what we get is every solution can be written in the form yp plus our homogeneous general solution. So then y is a solution to the non-homogeneous equation y double prime plus p of x times y prime plus q of x times y equals f of x. If and only if y can be written in the form y equals our particular solution, yp, plus c1 times y1 plus c2 times y2 for some constants c1 and c2. So again, here the implication goes both ways. If it takes this form, it is a solution, and if any solution must be able to be written in this form. So we call this the general solution. So y equals yp plus c1 y1 plus c2 y2 is the general solution. So in the next couple of videos, we'll learn a couple sort of rough techniques for finding a particular solution. And then in the videos for next week, for sections 5.4 through 5.7, we'll learn more official ways to find that particular solution and therefore the generals and then the general solution.